got some circular motion questions to do for a student at the office, but I'm going to record it, and hopefully if I explain these things very well, I'll put it up online and other people can benefit from it if they have similar questions. So the first one that we're going to look at, I haven't actually previewed these yet, but these were given to him as homework, and he had some basic questions, I guess. So here we go. With circular motion, we have to think about what's causing the thing to move in circular motion. So centripetal acceleration, usually expressed as like, sorry, this tablet is new, so I'm going to be fighting with that. If we have like acceleration centripetal, that's going to be v squared over r is one way to understand it. We can also have acceleration generally understood as like the change in velocity over time. And the thing about circular motion is that it's not like, its centripetal acceleration is not like a force unto itself. It's caused by other things. So like your teachers in school may talk about a bucket being spun on a rope. The thing that's causing that bucket to move in the circle is the string or the rope, right? So there's a force of tension. Like if you have a bucket here and you're swinging it in a circle, there's tension here in this rope and that tension is causing it to move inward. Like if the velocity is going that way initially, but this tension is pulling back inward, the overall motion is going to arc this direction because the inertia, the velocity that's keeping it going in this direction is going to want to push the object there, but the tension is wanting to pull it inward. So those two come together and they push it kind of in this direction, but when it gets to this position, the bucket is no longer moving in the upward direction. The velocity is now turned. It's moving in that direction, and the tension is still going inward. So that's what causes it to arc around. And when we talk about acceleration of centripetal motion, we're going to be associating this with other accelerations and other forces. So in this one, it was a force of tension, and we would use mass times acceleration here to find what the acceleration is, but we can set that equal to the definition of acceleration in the context of circular motion, depending on what the questions are asking. So let's go ahead and take a look at what this question here is designed to ask. I'm not sure, there are no page numbers apparently on these, so I'm just going to assume that this might be question 1. We'll see. So what do we have? We have direction of acceleration, velocity, car, so just conceptual. Car on an oval track starts from rest at R, moves clockwise, so clockwise is going to have us moving in that direction. Around the track, it increases its speed increasing its speed at a constant rate through t, so our velocity is increasing until we get to point t. So it might start out very slow here, and then it's increasing its rate of speed. Fine. Then travels at a constant speed until it returns to r. So every point along here is a constant velocity until we get to here. So this is the only position here where the velocity is increasing, but we do still have accelerations here, because remember, an acceleration is a change in velocity or a change in direction. The velocity can stay constant, but the direction changes, and therefore the acceleration changes, because remember that velocity is a vector. I'm just going to tangent out here. Velocity is a vector. A change in magnitude or a change in direction is an acceleration. So even though the absolute magnitude might not change in these scenarios, the direction is changing for our velocity, so we are going to have an acceleration. And if you think about it, being a vector, it has vector components. If the velocity is going straight down, there's no horizontal component to it. So we would say like velocity in the x direction is 0, and the velocity in the y direction is whatever it is. It's let's say 5, who cares? It's whatever the quantity is. But then as it goes around and changes direction, let's say the net velocity is now in this direction, it still has a component of it in the velocity for the y direction, and it has a component in the velocity of the x direction, and those come together. You do a little bit of trig, because this is really a triangle, right? You do a little bit of trig there, and you can find out what the magnitude is in the x and the y. So if it changes direction, the x and the y velocities are changing in their magnitude, which changes the overall direction of the velocity vector. But anyhow. So what's the actual question here? The points given in the table indicate the direction of the velocity and the acceleration of the car. Okay, that's pretty simple. I see that this student did his work here. Use the direction labels in the Rosetta below. J for no direction, K for into the page. Well, we should never use a J and a K in this situation. L for out of the page, no. M for none of those are correct. Okay, so let's take a look. So he says at point S, the direction of the velocity is C. The velocity in all these situations is going to be tangent to the curve. So at point S, or velocity should be going in that direction, so you got that right, yes. Direction of acceleration. So oddly enough, on these straightaways, so this is a straightaway. This is not a circular path. This is a linear path. Only on this hemisphere and on this hemisphere, from here to here, the radius of this circular path is from here to here, and that is your circular path. On these straightaways, there's no radius, right? This length from here to here and here to here is different. So those are not circular paths, and therefore the acceleration is in the direction of motion only if the velocity is changing. And from R to T, the velocity is changing. So at position S, both the velocity and the acceleration are in the direction of C. So this should be C. At point U on the track, the velocity again is tangential, so the velocity should be in the direction of E, and it is a circular path. So and on circular paths with centripetal motion, the acceleration, remember, is always inward, because the net force is inward. The friction, the tension, gravity, whatever is pulling it inward. I guess in this scenario it would be friction. So the acceleration is inward, and that would be towards G. So he got those right. At point V, the direction of velocity again is tangential. Tangential. I can't say that today. So it's going to be in the direction of F, and the acceleration is going to be inward around the curve, so that's going to be in the direction of H. So you got those right, good. Point W, remember this is moving at a constant velocity around the track. The velocity is in the direction of G, but the acceleration is not upward because this is a linear path. It's not circular. There is no acceleration, so M is going to be our answer for the acceleration at that point. There is no acceleration. Or I guess J for no direction. Because there is no acceleration, so it has no direction. So we put J. And this didn't understand that earlier, that these were going to be straightaways. Again, it's moving clockwise, so tangent to the curve, velocity is in the direction of A, and because it is curved, the acceleration is inward toward the center of the curve, so the velocity is in the the acceleration is in the direction of C. So A and C are correct there. So direction of velocity is always tangent to the curve, and acceleration is always towards the center of the curve, if indeed it is on a circular path. These straightaways from R to T and along W, those are not circular paths, so they do not have an acceleration towards the center. At point S, we have an acceleration because remember the question said that they were increasing in velocity in terms of its magnitude, and along T, U, V, we have accelerations inward because it is now along a circular path. But we do not have a change in magnitude for our velocity. Let's go ahead and take a look at our second page here. I'll bring this to the center. Shrink that guy down. Actually, pardon my futzing with OneNote here. I love OneNote, but the controls are somewhat kind of wonky for me. Alright, let's just zoom in on this. So, circular motion. In the movies, you see space stations, artificial gravity. They look like big donuts. Okay, yeah, like 2001 Space Odyssey. I'm sure there was one recently. In fact, in one of the most recent episodes of the Boba Fett series on Disney Plus, they used a circular planet. It was awesome. There's a book called Ringworld, and I'm sure they stole that idea from there. But anyway, they look like big donuts rotating on an axis. Yep, just like that. People walking on the outer rim on the inside, turning the space stations of gravity as if they were on Earth. How does it simulate gravity? Yeah, so remember that the person standing here on the inside of this space station, so you can see the figures here, these are their feet, and their feet are on the outer edge there, and even though this person here would be upside down to these people here, they're still able to stand on the outside edge because their velocity is tangent there, and their acceleration is inward. Is that gonna be correct? Yeah. And what's causing that acceleration? It's the normal force. There is no gravity in this situation. There's a force normal. So this inward force here, let me see if I can increase the thickness of my pen. So there's a force normal. Ooh, too thick. And that normal force is what's supplying the centripetal motion. So force normal is equal to mass times acceleration here, and the acceleration is going to be our centripetal acceleration. And the force is supplied by the contact between the person and the outer edge of the space station. And as the space station rotates, the person is rotating at the same speed. They've got some friction between their feet and the outer wall of this thing. It's curious, though. Yeah, just trying to think of the mechanics of how this would start spinning and what you would experience as it sped up. Because you wouldn't necessarily feel the acceleration right away. And if somebody was like hovering in the air, they would just stay stationary and the ship would rotate around them. They would actually have to come into contact with the surface of it to be sped up with the space station. And when they're both moving at the same velocity, they'll be moving together around the space station. And that velocity that the person has would be pushing them into the edge and creating that normal force, and thus the acceleration. But anyway, let's see what our student said. So the station is in Earth's gravitational field, and the station is rotating around the Earth, giving an acceleration towards Earth, causing the station to have artificial gravity. That is not correct. This space station can be out in the middle of nowhere. It could be like billions of miles away from any massive object that would cause any significant amount of gravity. There is still gravity in space, of course, but if you get far enough away, the effect of gravity becomes negligible. And it's not anything exterior to the space station that causes the sense of gravity. So this is not correct. It's the circular motion of the person and the space station that gives the sensation of gravity. It is not true gravity. It is a sensation of gravity. Remember that we only feel the effect of gravity because we're on the Earth, right? If we elevate ourselves off the Earth, we begin to fall. And we experience weightlessness, maybe air resistance if we're in air. But the normal force between ourselves and the Earth is what we experience as weight. But in this scenario, our weight would come from the contact between the outer edge of the space station and our feet, and the fact that we are moving, our body would move with a velocity. We're basically falling into the wall of the space station, and because that space station is rotating, it keeps our velocity moving. If that space station was not rotating, we would eventually lose the sensation of gravity because we would not have a velocity in that direction. I hope that makes sense. Yeah, it's essentially because of our tangential velocity that we keep getting pushed. It's pushing into the wall. Imagine you have like a curved track, and you drop a marble into the curved track. The curvature of the track is going to keep that marble moving, and the marble is going to it's going to say, oh, there's a wall here, and it's going to move in that direction. And then it says, oh, there's a wall here, and it's going to move in that direction. And it's going to say, oh, there's a wall here, and it's going to move in that direction. That's essentially what's happening here in the space station. Every time your body wants to move this direction, the space station is moving with it and saying, oh, you can't move in that direction. I'm going to push you back inward. And that's going to give us that sensation of gravity. It is not true gravity that is causing the motion here. Don't confuse the two. So we do not have an exterior body there. The Earth does not need to matter in this situation. In fact, it does not say that the space station is near the Earth or any planetary object. All right. Roller coaster has a dip with different radii of curvature. The same roller coaster car arrives through each dip at different speed. Magnitude of force at the track, the roller coaster track, and card at the bottom of the dip. Okay. So these are representative of different dips then. So here we have a radius of 60 meters. Here we have a radius that is smaller, 30 meters. And here even smaller, 15. So it's the same scenario as what we've got here in the drawing. The velocity of the cart as it goes down the ramp is going to be tangent to the curve at each point along the curve. And then the radius is constant. Yeah, it's got this circular radius here. But anyhow, let's see what our scenario is. So remember, the basic equation for acceleration centripetal is v squared over r. And I hope that's what our student used here. So if the velocity is 16, yep, that is indeed what they did. V squared over r, v squared over r, v squared over r. So it does look like the student used those numbers correctly. That is all we need to do for this question. Here is jam each of these scenarios into that equation. Rank the numbers in increasing or decreasing order. You'll notice that scenario 1 and scenario 3 are equal, even though the numbers are different. That's because you can do proportions in this stuff. You can make them proportionate so that when you do the v squared over r, it reduces to the same fraction. All right, I'm not going to go through that one because he's done it correctly. If the person would feel like they weigh more or less than they would normally do. Yeah. So if you're going through a dip like that, you would experience an increase of force as you approach the bottom. Because remember, there's a force of gravity pulling you down here. So the normal force of the track is reduced as you go down, because the normal force counteracts the perpendicular force of gravity here. Remember, it breaks out into vectors. So the more vertical your movement is, the less the normal force will be. But as you get to the bottom, not only is the cart or your body having to counteract the effect of gravity, but it also has the added effect of being circular motion. So there's going to be a force normal here, and that force normal is going to be the combination of the gravitational. It's going to counteract gravitational, but it also is going to be consistent with the centripetal motion here. So the combination of centripetal motion and gravity is what you'll feel at the end, or at the bottom here rather, thereby compounding the effect, making you feel like you're heavier, essentially. So you feel heavier at the bottom than you do at the top, of course. Yeah, and the normal force is the cause of the circular motion. Pretty simple conceptual page there. Let's go grab another. How long is this video getting? 20 minutes, man. All right, I'll try to go fast. Next page, 6 rockets just had their engines turned off. All of the rockets are aimed upward at the same angle. Speeds are different. That's important. So same angle, different speeds. All the rockets are same size and shape. Okay, so holding that constant, carry different loads, so their masses are different. Specific mass and speed for each rocket is given. Awesome. In this situation, we're going to ignore air resistance, of course. It is an introductory physics class, after all. At the instant when the engines are turned off, the rockets are all the same height. Fine. Rank these model rockets from greatest to least in the base of horizontal speed at the top or maximum height. So, are we understanding this then? Okay, horizontal speed at the top. Are we expecting this to be projectile motion then? So like they did launch, and then these things are like at the top of their launch. Horizontal speed at the top, at the maximum height of what? At the maximum height of their trajectory after launch? I have to imagine that's the case. So anyway, so they launched at an angle. And it's going to start doing a projectile motion. Projectile motion could be circular motion, but it's not truly, because a projectile could be something like this, like a parabola. It's more parabolic motion than anything. But this is the circular motion unit, so it's kind of confusing why the teacher included this. But let's see what we can do. So we have a velocity and a mass for each. Let's see. Do they have... Yeah, their speeds differ. Okay. Is this a trick question? They're asking about horizontal speed at the top. If they're all launched at the same angle, their horizontal speed is going to be a function of the angle, theta. The launch velocity is the net velocity there, and then we have a velocity in the x component and the velocity in the y component, the x and vy. If their angle is all the same, we can do some trig here. We can do Vx equals the cosine, or sorry, v, the launch velocity, we'll call that v naught, times the cosine of theta. And since the cosine of theta is the same for all of these things, so we can just label it as a constant, let's call that k. So the only difference between these things is then, like this one here is going to be 25k, 30k. So they're directly proportional with that. Their mass in these scenarios, they're all fighting gravity equally. It's in grams. Our regular thing is kilograms, so 0.8 kilograms, 0.5 kilograms, 0.6. Let's just take a look at these three and see what we got to do. Kilograms. So what is this velocity going to do? They aren't going to have the same, unless these are circular motion. If these things are moving in circular motion, they might have the same horizontal speed. Just had their engines turned off, they're aimed upward. Sorry, moved the page, there we go. I wish there was an easier way to recenter. And if anybody knows a good way to recenter a page on OneNote, let me know. Alright. Greatest horizontal speed. So you could reason your way through this, like if you have a high velocity and a low weight, then your horizontal speed in this scenario is going to be like, but gravity is going to be constant for all of these things. But net velocity, so hold on. Does mass even matter? In this scenario? You can tell I didn't review these beforehand. I'm not sure that mass even matters. Have zero horizontal speed at the top, that's false. Have the same horizontal speed at the top. That would only, let me read through this. They reached the same height? How is that possible? Something is missing from this question. So what this question is suggesting to us is that we've launched 6 different rockets of different payloads and at different velocities, but they've all somehow managed to reach the same height at the same time? They had different initial velocities at the same angle. That's not possible. Okay, the amount of time must have changed. Okay, because it would take different amounts of times for these things to reach the same height, given different velocities and masses. Mass I don't think matters in this scenario, yeah. I'm gonna stick with that. That mass in this scenario isn't necessarily going to be very important. In projectile motion, if we wanted to calculate the vectors on this stuff, we would have to know the angles, of course, and the y velocity is going to have an acceleration on it, but the x velocity is not. The x velocity is constant through the projectile motion, because if you think about it, if these things are launched off of a planet or any kind of significant surface, So here's the planet. They launch this way. The only reason they begin to bend like that is because the y velocity is changing, but the horizontal velocity is not. Let's dig into that a little bit. Make sure that you review projectile motion for this one. So the velocity in the y direction is equal to the original velocity times sine of the angle of launch, and the velocity in the x direction is equal to the original velocity times cosine of the angle of launch. Because remember, if we have that angle of launch, theta here, Vy is that height and Vx is the base of the triangle, and your launch velocity is that. Remember that sine is opposite over hypotenuse, so sine of theta is equal to Vy over V naught. You multiply that over and you get V naught sine theta. And the same thing is true for cosine adjacent over hypotenuse. And then if we think about the scenario on the surface of the Earth, we've got a gravity here, an acceleration due to gravity. But that's only acting downward, right? So anything in the vertical component is going to have a change in velocity because it has an acceleration acting upon it. So Vy is going to change depending on the time. But Vx, there is no horizontal acceleration in these situations. The acceleration in the x direction is 0. So the launch velocity in the x direction is constant. So if we consider these scenarios where the Vx is a function of the initial velocity times cosine theta, anything that has, like these guys here, 20 and 20, these guys are going to have a Vx that is equal. So Vx for C and Vx for D are going to be equal. The mass here I don't believe is going to matter. You might think it does, but since we already, like whatever the engine's output is enough to get this mass to that velocity, then it shouldn't matter. So anything that has equal mass, or equal velocity rather, should have equal horizontal speed. So the one with the greatest horizontal speed is both B and E, unless I'm completely wrong here, B and E. You might infer that the smaller mass is going to be trucking along faster. So if anything, I would say E is the fastest, then B. Number 3 should have 25. I would say F, then A, then 5 and 6. I would say D, then C, if I were to rank these at all. But I would also go so far as to say that B and E may be equal, F and A may be equal, and D and C should be equal. Because if these things are launched at these velocities, then their masses don't matter. Because whatever the output of the engine is, was enough to get that mass to that velocity. And once it's moving at that velocity, it's constant in the horizontal. Alright, and that's what he said here. Gravity is only affecting where it was launched and landed in the y direction, in the y axis. Mass has no effect on velocity, time, or distance. Yeah, at least not in these scenarios. Very good. And I believe there's one more page. Pull this over here. Zoom out. Make it big. Alright. I got some cannons. Picture below the cannonballs, 2 different masses projected upward and forward. Cannonballs are projected at various angles above the horizontal, so we have differing angles and we have differing masses. Again, mass shouldn't really matter in this scenario. And yes, we are indeed doing projectile motion, which is related to circular motion, but it's not always circular. It's a projectile, it could be a parabola. Okay. same vertical component of velocity. So that means that our horizontal velocity is the thing that's changing. From largest to smallest according to the time the balls are in the air. So how much hang time do they have? Because the y velocity is the one that determines how much time they're in the air, these things should have the same amount of hang time. It doesn't matter what their mass was because they're all reaching that same velocity, and acceleration due to gravity is constant no matter what the mass is. So they will all fall at the same amount of speed with the same velocity. So they'll all hit the ground at the same time. So all times are the same. Yep. Balls all have the same Vy. Yep. Exactly. And apparently that is the last question. Excellent. That was just purely conceptual in nature. So for whatever reason, the teacher is including circular motion and projectile motion in a single unit. That doesn't seem terribly great to me. What I would recommend for anybody who's hoping to study this stuff is to head on over to physicsclassroom.com, go through the circular and satellite motion unit, go through the projectile motion unit as well. If I'm trying to review myself on these things, this is my first stop. I go through the tutorial section. I do not use the Minds on Physics. I do not use the concept builders because I do not find them incredibly useful. So circular and satellite motion is great. The motion in two directions is great. I think, where is projectile motion going to be? Let's see. Gravity, circular motion, weightlessness. Do they have projectiles in here as well? It's easy enough to Google. Projectile motion. There we go. That was under, 2 dimensions. That's what I thought. So notice that these are not circular in nature. At least not totally circular. So I would recommend that you review this unit and the circular motion unit. That is it for today. Make sure you check out my other videos.